we go. So right here in the middle is my PhD advisor, Tobin Marks, and his PhD advisor is here on the left. And Fred Basolo is a very famous inorganic chemist from the university where I went to graduate school in Chicago. And they had this tradition that they had meetings on Saturday mornings, and you could only use a chalkboard. And the start of the meeting, the first thing you had to do was draw a map of how you got to where you are. So that's what I'm going to do, but I'm not going to use a chalkboard. So I grew up in Houston, Texas, and my parents were scientists. I'm incredibly lucky. I feel both of my parents were first generation college students and then first generation PhD students. So I had all the knowledge of everything you have to do well in college, and from people who knew how important it was to know how to do all the things. And so I feel like I got, a lot of information from them about how to pick a good school. So I ended up going to UT Austin, and I got a degree in chemistry, biochemistry, and applied math. Mostly I just didn't want to leave college. If I'm honest, my second year of college, I figured out that I could have graduated early, and my boyfriend told me that he thought that I should stick around. And so I did, because, when you're 20, you're stupid. But anyway, in the long run, it was good for me because it let me sort of explore and try different areas of science. And I actually completely changed my focus from being sort of biomedical when I started to being very physical and math oriented by the time I finished. And then I just moved straight north to the city of Chicago. I mean, not exactly straight, but close enough. And I did my PhD 50% theory, 50% experiment. So the person I showed you before, Tobin Marks, he was my experimental advisor, and Mark Ratner was my theoretical advisor. They had 50 joint students by the time I joined their groups, but I was the first one to actually do 50% theory and 50% experiment. After my PhD, I went straight over the ocean to Sweden to do a postdoc. And I ended up focusing on theoretical chemistry in particular. So you've probably never heard of it, but Lund, Sweden is the birthplace of some of the fundamental quantum mechanical equations that and the implementation of them into computational codes that you're probably using if you're calculating anything about molecules. In particular, it's where CCSD and the original CI sort of expansion methods were developed. So I worked on light harvesting dyes there, and then was way too American and needed to come back to the States because I was feeling frustrated with cultural things about how science is done there. So I came back to Washington, DC and worked at the National Institute of Standards and Technologies for 3 years. So NIST is a fully federal lab. If you have any experience with some of the Department of Energy labs, it's a little bit different. It's much more like a military base. The land is federal, how you work, everybody's a federal employee. And so that comes with both pros and cons. And so after a few years, I was really looking to interact with students more again. We had this community college program, actually, which is, I guess, relevant to you guys, where we would try to have students from the local community college come to campus and do research projects. And they never could get a background check in less than 6 months. And I'm sure all of you know that your life and your schedule and everything are changing way faster than 6-month timeframes. So I just couldn't ever get students to actually come and work with me on campus, and I found that frustrating. So, all right. So from there, I came to Lehigh. I'll show you, it's up here in Pennsylvania. And I don't know why that's not in here. So I just thought I'd show a bit of the breadth of the chemistry that I've worked on over my career, because as I said, I started pretty biological. Literally, I was looking at, these are yeast cells and them reproducing. So I took photos of yeast having sex all the time. And that was my undergraduate research project. And then I sort of worked on structural biology and sort of structural biological mimics. And then I went to graduate school and I focused more on materials. So I worked on what are called dielectric materials, and really these are structures that exist in your computer and in other devices to prevent buildup of charge and fires in your computer in particular. So we were looking at how they break and sort of how to stop them from breaking in ways that create fires. And again, I did this both with theory and experiment. And then when I went to work in a more sort of theoretical group, we picked molecular targets which were interesting for light harvesting applications. So these are dyes that are used in solar cell devices. At the National Lab, I spent a lot of time working on methods to reduce computational cost. So I know the Lopez group has some projects in machine learning, so similar kinds of techniques of using input structures to create faster paths to calculating properties of large sets of materials. So Lehigh is in Pennsylvania. This is our lovely campus. We're a small university. We have about 5,000 undergrads and about 2,000 graduate students. I'll just skip this. This is a promotional slide. But just to show you where we are. So here we are in Bethlehem, Pennsylvania. So it's an hour to New York, or an hour and a half to New York City and an hour and a half to Philly. And you might have heard of us if you're into music. It's the host for Music Fest, which is one of the largest music festivals here on the East Coast. So I didn't have anything about my current research. I guess I'll just say what my group does now is we work on sort of disorder in materials and how that disorder affects catalytic and photochemical properties of them. And if you have any specific questions about that, I can take a second and pull up a slide that shows sort of everything we do. But I figured it might be better to start with some of the path stuff. If you have any questions about my path in particular or things you're thinking about your own path, I'd be happy to answer them. And I feel like let's just be informal. So just unmute yourself and call out or put something in the chat if you can't unmute yourself, like Daniel.
I can start. Can you tell us about maybe the challenges that you had in Sweden and academic science there, and what made you want to come back?
Sure. So there's two things. The way they teach college classes in Europe is very different than the way we take college classes here. So most of the time, if you're a full-time college student in the United States, you take multiple classes at a time, and therefore you have to balance how much are you going to study for chemistry versus how much are you going to study for math versus how much are you going to spend time on English, right? And even if you are a student in the US who's not taking multiple classes, you probably have a job or an outside life, and you're balancing all your life responsibilities and your job responsibilities with taking classes and getting good grades. And in Europe, often they take a single class at a time for just a few weeks. So rather than a 14-week semester, they take a class for 6 weeks at a time, and they only take that class. So for instance, if you take physical chemistry, you take the lecture part in the morning. So it's like a summer class, basically. You take the lecture part in the morning, you do the lab part at night, and you barrel through all the material really quickly. If you've ever taken a summer class or tried to teach a summer class, what you'll learn really fast is that people don't learn anything, and they don't internalize the information. And for science in particular, that's really bad. So what I found is that the students I worked with were less well prepared at the level that they were at than I expected. So they didn't remember things they had learned in coursework. And they also hadn't learned one of the most important skills in research, which is how to multitask and balance working on multiple things at once. And so they didn't have any of the sort of coping mechanisms I would have expected of a graduate student for like, okay, when I come in the morning, maybe I shouldn't check all my calculations first because I know that that's sort of a mindless task. Maybe I should write, a page of my paper first and then check all my calculations. Or maybe I should, not stop and have coffee for 2 hours with someone, but I should work, on my research in the morning when that's when I have the most energy, and I should have my coffee break with my friend at 3 o'clock in the afternoon when I'm already tired anyway. And so that part for me was the biggest struggle. The other struggle is the way they fund science in Europe is much more, the pools of money are much smaller because the countries are smaller. And so there's much more shifting winds of what's popular. And so you watch people's careers that they sort of work on something water related and then work on something solar related and then work on something else. And that's because of how their funding works. And so because of all of those things, I decided to come back to the US. I guess I'll say Sweden in particular also had an issue where they're a culture of consensus. So when you have a disagreement, everyone has to agree by the end of the discussion. And in science, there's lots of times where there are no good options or there's no best option. There's just differingly bad choices to be made. And I found as an American it incredibly frustrating to not be able to say, let's just agree to disagree. Like, it's okay. I don't dislike you just because I don't agree with you. So that was I was much too American to stay part. So.
Cool, thanks. Maybe one of the students or participants has a question.
It really can be anything.
Like compared to like you said that you worked for a national lab, like how's that different from like academia and like the pace of like being a professor?
So the pace is quite different. I'd say working at a national lab is very similar to being a postdoc in that, again, a fully federal national lab. If you work in a Department of Energy lab, you also have to find funding for your salary. In a fully federal lab, so any of the military labs or NIST or OSHA or NOAA, those are the ones that are fully federal, your salary is paid for. So you just have to do good research. So, you define the problem and you find the resources to work on it, but you as an individual don't have to find money to pay your salary. Because of that, and because of the red tape that is involved in the government, things move a little bit slower. So I'd say on average, people at NIST in particular, who are highly productive, publish 4 to 5 papers a year. Most faculty members at, I'm even at an R2 university, so it's a slightly smaller university. There's more focus on teaching. That would be glacial pace of publishing papers. So even the research is a little bit slower. And then at a national lab, your job is research. There is a bit of service to the lab and mentoring of other people in the lab. But if you choose to stay in the sort of technical track of the national lab, really your only job is research. So 80 to 90% of your time is just spent on research. And a faculty member at any university, there's teaching, research, and service. And so you're balancing a lot more things, which just means, more stuff to do. Kind of. But I would say for me, the pace at the national lab was frustrating. Everything took 5 times longer than I would have liked it to. And NIST in particular for synthetic work was frustrating because it's federal land. So you can't do certain experiments. You can't buy certain chemicals because it's federal land and you can't store that on federal land because it's illegal. So there were a few additional issues because of that. Yeah.
So thank you.
All right, I have a question. So what would you say your favorite research project is right now? Can you hear me? Great, all right.
That's hard. Okay, well, I found my slide, so I'll show you that. My group works on a lot of stuff. There we go. Okay, so this is what I would say is our current focus. I think everything falls into this idea of disorder in materials. And then we use the models we build to look at photochemistry or interfacial chemistry, so catalytic chemistry. And then I'll just show you, these are the people that actually do all the work, right? So this is my group. I think right now, one of my favorite projects is, so my graduate student Gil up here has developed let me get a pointer again. Gil up here, he's developed a bunch of models of titanium dioxide nanoparticles. And we're starting to use those models to model interfacial chemistry. So my postdoc and one of my undergrads, Rob, are using the models that we've built to actually calculate catalysis on nanoparticles. And what we're finding so far is that everything on a particle is completely different than, sort of periodic surface models that people have studied before. So that one's been really fun. The other project that is particularly fun is Zach and Gabe up here. We're working on disorder in organic crystals, and we're looking at how vibrations in those crystals affect their electronic properties and their conduction. I never thought I would work on this again. It's a project very related to actually what I did in my PhD, and I probably wouldn't have gone back to the topic so early, but Zach joined my group and he's really interested in developing new statistical mechanics models. And so he sort of spearheaded all of this, and we're getting to the point where we can actually look at sort of thin film structures of organic materials in really accurate calculations, which is also really fun. So I'd say right now, those are probably my two favorite.
And I guess another question, like how new is the field of studying nanoparticles? Is that like not a lot is known about that, or?
So lots of people study nanoparticles computationally. The problem for everyone, including us, is that the size of particle you can calculate with high level methods is very small compared to what is used in an experiment. And so you need to be really clever about how you build your models. It depends on what you're trying to model. This is always true. So my group would laugh if they could hear me right now. You know, how you build a model matters. How you draw a molecule matters. What you think is happening in the system is an initial guess that you're giving the computer, and it sort of sets off your exploration in a project. And so what we've seen in the nanoparticle space is that the choices people have made are not maybe good for where they're applying their models. So they're modeling things, and if you're modeling a tiny nanoparticle that only has 10 atoms in it, you can model that incredibly accurately. If you're trying to use a 10 atom cluster to model a nanoparticle that's 100 nanometers in size, maybe that's not such a good thing to do, or maybe you can do it, you just need to be smart about it. And so what Gil has done is found 6 different ways to build nanoparticles that give us different kinds of particles. Each one is better or worse for different kinds of applications. So if we want to model catalysis, we need to use one kind of particle. If we want to model photochemistry, we need to use a totally different particle.
So it's as much a study of the methods you need as it is the actual thing, right? Yeah. That's interesting. So yeah, all right, that makes sense.
I have a more general question. So you have like an advice for the students that are studying in the computational chemistry field?
Mm-hmm. I mean, my first piece of advice, so I'm actually doing a workshop for students who've never done computation tomorrow, and I'm going to teach them how to use the Linux command line. And so the first thing I always say to them is, it feels really hard. You have to know 100 things to be able to do computational chemistry. So it feels really hard at the beginning. But trust me, I don't know a single student. I've worked with hundreds of students. I've never had a student that after 5 or 6 weeks isn't able to do everything that they need to do to run the calculations. So I'm sure, I think Stephen was saying that you guys were just running your first calculations this week, and I'm sure it feels overwhelming. And, you know, that's partially just because you have to start doing and get practice in to get good at it. It's like lots of skills, you know, you don't know how to throw a baseball until you practice throwing a baseball. You don't know how to run a calculation until you just run 50. So just keep going, it will get easier. That's the first thing I would say. Career-wise, what I would say is this is the time to explore, right? You're doing a computational summer program. Maybe you won't end up being a computational chemist. So I can point out, so on this slide, so Ice is an undergraduate who just graduated from my group, and she's going on to graduate school at Princeton. She just started there actually last week. But this set of girls here were part of a program that I run every summer. Kira is going to work in a biochemistry lab because she didn't love physical chemistry research. Katie has decided that she wants to be a dentist. Ing is going to stay in my group because she wants to go to graduate school, and Athena is going to medical school. So all of the things you're doing during college or during this time frame are collecting information about what you might want to do in the future. And if that isn't computational chemistry, that's okay. You got information about, you know, whether this was what you were interested in and whether or not you want to do research. I would say, you know, whatever your processes you're doing in the lab are completely applicable to any experimental project you might do. So the process of learning new tools and then trying to apply them and then probably redoing what you did because there might be a mistake. All of those are typical research tasks. So maybe think about whether you like that process or not, even if you don't end up falling in love with running, calculations. The other thing I would say is there are no jobs nowadays that don't include using a computer at a high level. So take this as an opportunity to learn more about how computers actually work fundamentally. Using the Linux command line can really be helpful for gaining an intuition of how computers work. I have actually a master's student who worked for me when I was working in Sweden, who ended up in the financial sector in Europe, and she creates models of financial banking systems, but she has such a better understanding of how computers work than a lot of the people she works with, that she ends up getting a lot of high level tasks that they wouldn't give to someone who's as junior as she is. So take this as an opportunity to learn skills that will be useful. Tons of people and companies in all different sectors use coding and scripting to analyze their data. Looking at big sets of data sort of is a talent. And so use this as an opportunity to practice that. Yeah.
Great questions. Any other ones we want to ask while we have Lisa here with us? Okay. Well, if not, yeah,
thanks. An email later if you think of something.
Yeah. Okay. Yeah. Thank you. Thank you for that. So I took a covert, what do you call it? Screenshot of us just about a minute ago. So I'll send that out so y'all have it. Thanks for contributing again, and thanks for participating, everyone.
Yeah. Have a wonderful summer, guys.
Yeah. Thanks. Okay. Bye.
Thank you.